All right, we're going to start with a little football problem. So we have somebody that's kicking a football, and there's a field goal that's 15 feet high, 25 feet away. So they kick the ball. It goes up initially at 80 feet per second at 60 degrees, and it's going to basically do this action. All right, and it's going to land in the stands. So stands start 55 feet away and they go up at 45 degrees. And so we want to know, where does the ball hit the bleachers, where we straighten out the bleachers at this 45 degrees. We're not going to worry about the stairs and all that stuff. Okay? So what are things we know? We know the initial velocity. Therefore, we can... and we know the acceleration. We got gravity, and we'll presume we're operating in the ubiquitous vacuum. All right. So let's just start with, let's break down the initial velocity. So since we're in a vacuum, whatever velocity this is in the x, it's just going to go, 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 go. All right. So that's very simple. That's what we have here. dx equals v0x, the initial velocity in the x, times time. Okay. That's not very exciting. So let's just start with, if we look at V0, let me just come up here. V0 in the x will be 80 cos 60. That works out to 40. So it's initially going at 40 feet per second in the x, and we can just stick that in here, and so as a function of time, bam, we know where it is. All right, V0y, that would be 80 sine of 60, and let's see, that works out to 69.28 feet per second. Okay, so we broke this up because we're going to have constant acceleration in the y and no acceleration, which is constant, in the x. All right, so let's think about this. If we look at things we have, we know the acceleration. This thing's going to go up in the y, and we know the initial velocity. So we can figure out where this thing is in the y as a function of time. So let's just write the following. H, the height of the ball, starts from ground, call that 0, plus 69.28 times time plus 1/2. Now we're in feet, so that acceleration is minus 32.2 feet per second squared times t squared. So there's height all the time, and we're asked, where does it hit? So this is in terms of what this problem is, it's a position problem. What's the position where the ball hits the stands? And then we have dx, the distance it goes along the x is simply 40 times t. So if I look at this problem, I have 1 unknown, time is an unknown, distance in the x is an unknown. I need 3 equations. So that's all that's really left of this problem. I need to find a third equation. And now let's just notice, as when this thing hits relative to this spot, whatever this is in the x from here to here, it's the same in the y. So that says when this thing hits, whatever it is in the y, okay, dx, so here's 55 feet plus a little x more, this y equals that x. So, but I'm measuring from here. So this distance minus 55 equals that x, which equals that y. So, bam, equals h. I now have 3 equations and 3 unknowns. So this is one of the typical strategies in this. Look at what you have to work with, which we've done here. The x is really simple. The y, very common equation. And then try to see, is there some way you can relate x and y? And that gives you 3 equations, 3 unknowns. So if we apply this, go to solve it, I'll note we can simply stick this into here. So to solve this thing, we'll say, sticking this into there, 40t minus 55 equals h, equals 69.28t little ugly. Minus 1/2 32.2 t squared. One equation, one unknown, solve for t, come up with 2.969 seconds. All right, stick t back into here and here. This will give us the x, that'll give us the y. So if you do that, dx is 118.76 feet. The height, subtract off 55, is 63.76 feet. Of course, we could have stuck t into this equation and got the height directly that way. More than one way to skin the cat. All right. We'll have more problems here in just a moment.